Okay, on this particular example, okay, we are now in the chapter 18, work and energy, and for this particular example, we are focusing on the conservation of energy. And on this particular example, we have 30 kg. This is released from rest when theta equal to 0, and we need to determine its angular velocity when it is at theta equal to 90 degrees. Okay, let's redraw. Okay, initially, I draw it a bit smaller. Initially, it is like so. Okay, this point there, and it is the initial position, and the final position or position number 2. What happen is it will like that. Okay, this is the final position, and here we can see that it is making an angle of 90 degrees lah. Okay, from here to here is 90. So should be 90 degrees. Okay, it is 1, it is at 2. Okay, from the conservation of energy, we know that E1 must equal to E2. So that is the principle. And in general case, what we'll have is PE1 plus any losses or any external energy involved, okay, friction as well. Then kinetic energy, the final kinetic energy plus the final potential energy. Okay, in this case, it is mentioned that it start from rest. So this one to the 0. Then as you can see physically, this is the this is at when theta equal to 0, it is at the highest position. So you have potential energy, okay, because you have some elevation, okay. And then in this particular example, we don't have any external energy involved, so either losses or any energy in, so it's become 0. And then how about the kinetic energy? And yes, we do have the kinetic energy because this it rotates downward. Okay. Therefore, here we will have something. And for the potential energy, when it reaches this point, and we know that the W is here, so of course it will have no elevation. Okay, so this part here become 0. Then what we have here is PE1 equal to KE2. Okay, what is PE1? PE1 is very simple. It's just that the W, okay, this is mg, and then the distance, the vertical distance from here, because point G initially is somewhere here, right? So it moved to this point. So let's say this is our H lah. Okay, and we can say that at point 1, with respect to point 2, the position of point G, it is 0.3 meter. Okay, so what we have here is uh, mg times 0.3. Okay, because point G is going down with a 0.3 meter, similar as this radius. So how about the kinetic energy? The kinetic energy, we have two parts. We have the translation, and then we have the rotation. And for the translation, we have half mv g, okay, g square plus half I g omega square. Okay, we know what is the value of m. Vg, we need Vg is omega r. Okay, r is known, which is 0.3. So r is 0.3. Omega we don't know. And don't forget that this, if you replace it, it should be square. And then how about on this part here? Ig is, okay, half mr square. So m is known, r is known. Okay, so you can simply calculate this Ig, which is to be equal to 1.35 kg meter square, okay, for the Ig. And if you plug in all the value, m is equal to 30 kg, G is 9.81, then rearrange everything, you will get this question. Equals 0. And finally, solve this, you will get, take the square root of these things. Okay. So omega will be 6.6 radian per second. That's the answer. Thank you.